Welcome to Tomversations, a monthly conversation about technology topics with me, your host, Tom Hollingsworth, the networking nerd. And I wanted to dive into a bit of emerging technology in this month's conversation. It has an impact on some things like security. It's something you may not have heard of before, and I'm very excited to be bringing it to you. Are you a twin? Someone who has an identical copy of you running around somewhere? Same eyes, same hair. Maybe you are, maybe you aren't. But do you know what a digital twin is? A digital twin is an interesting new development in the world of modeling and analytics. Now, you've probably seen a digital model of something. I've made them before. In a CAD program, you can draw up a diagram or a three-dimensional representation of an object. Maybe it's a three-dimensional representation of a coffee cup. And you can get it pretty accurate. If you have a pair of calipers and some good measuring tools, you can make it look almost identical to whatever it was that you had originally measured. But what if it was completely identical? What if it was, in fact, a twin of a real-world object? Now, the term digital twin has been around a lot longer than you might realize. It was originally discussed in a book by David Geltner back in 1991 called Mirror Worlds. It took a little bit of development from researchers before they were finally able to bring the concept to life. And that happened at the Florida Institute of Technology back in 2002, thanks to Michael Greaves. Now, the term did not enter the workspace until 2010, thanks to NASA, where they used the concept of a digital twin to help them model spacecraft. So what is a digital twin? Well, it's a real-time digital copy of a physical object. What sets a digital twin apart from just a regular 3D model? Well, when you create this virtual copy of a physical object, you're also creating it with the data that that object contains and updating it. So let's use NASA's example for just a moment, because this is an interesting way to look at digital twins. A spacecraft is a collection of parts. It is a collection of processes. It is a thing that, when it does its job right, is completely inaccessible to us, because we launch it away from this planet and we send it out somewhere to learn things and to send us data back. And as we've learned over the years, space is a very harsh place for all kinds of technology. All you have to do is look up the number of subsystems that have failed on spacecraft that have been extended well past their natural lives. Voyager 2, for example, most of the subsystems on Voyager 2 have failed already as the electrical components start degrading over time. But how do you fix Voyager 2 when it's 19 light hours from Earth? So you have to wait 38 hours to know whether or not your course correction even worked. You don't want to invest the amount of time that it's going to take to fix a problem and then find out that nothing worked when it takes a day and a half to even make one command operate correctly. What if you could build an exact duplicate of Voyager 2 right now on Earth and test your commands or your fixes against it? And when you know something works and it won't crash the system, you can send the corrected commands or the corrected fixes. That sounds cool, right? We kind of do that now when we have modeled networking environments or development labs. Well, that works when it's a system or something that we have the ability to virtualize. But how do you virtualize a spacecraft? How do you virtualize a pacemaker? Trust me, you don't want to do an update to a pacemaker that causes it to stop working, and neither does the person wearing the pacemaker. So that's the idea behind digital twins. But more importantly than just creating an exact duplicate, a digital twin takes the data from the object that it's duplicating and updates the digital model in real time. One of the places that a digital twin is being used today is on autonomous vehicles. So think about your average modern vehicle that has autonomous capabilities. Most people will probably point to a Tesla. A Tesla is, among other things, a complete battery of analytics. The car can stream all kinds of real-time analytics data back to Tesla. It can update things like how much pressure the tires have, how much charge the battery contains, and what the predicted lifetime of the battery is. And it can even tell you if the windows are rolled up or down. What if you could take all of that data and plug it into a digital twin of your Tesla? What if that digital twin in real time could tell you what was going on with your car? Hey, we noticed that your tire pressure has been slowly being reduced over the course of the last 3 weeks. That means you probably have a slow leak in your tire and you need to get it fixed. Or we've noticed that your system seems to be braking 0.3 of a second faster than it should be. So the Tesla software engineers can take that code and they can tweak it to make the car perform properly. Except instead of having to do that on a production Tesla model that they have just sitting out on the back lot, they can do it to your car's digital twin to ensure that it will work properly before pushing all the software patches down. Another place that digital twins come in very handy is in security, specifically around things like IoT. IoT is a very challenging problem for most security professionals because we're used to security devices that allow us some modicum of control over the device itself, whether it's a command line interface or even a GUI where we can go in and create rule sets and implement policies and kick people off if they're doing things they're not supposed to. But how do you do that to an IoT device, which is running on a very inexpensive board or has very limited interfacing capabilities? Well, you don't. But if you have the ability to create a digital twin, you can create the digital twin, operate on it, fix it, or find ways to contain issues and then push those patches along. Think about something like, I don't know, a distributed denial of service attack. This is a huge problem that we're seeing growing more and more as we have bigger, better, badder connections to the internet. Some of the DDoS attacks that have happened in the last couple of years have reached the hundreds of gigabits of throughput, which is enough to crash almost anything. So what happens when you direct that kind of ion cannon toward a very small IoT device on the edge of a network? Well, nobody knows. And if it's a critical IoT device, you really don't want to do that to something running in production. But how can you guarantee that that exact device will behave in a way that you expect it to? Well, enter the digital twin. We copy the device using something called the digital thread, which is the most basic layer of a digital twin. We model that device, we update it with data from its twin, and we test on it. We hit it with the biggest DDoS we can imagine. We try to root around in the system and exploit it. And when we find a hole, we patch it. And we push the patch to the original twin. The original device updates with the new configuration information, and then it updates its twin in real time. There is a significant amount of possibility that comes from the idea of digital twinning. We've already talked about things like autonomous vehicles and spacecrafts and IoT devices, and even healthcare. But what about modeling things that are difficult to predict? You can model a supply chain, but if you create a digital twin of a supply chain, you can see what kinds of impacts that you can have on the system. And as someone who studied systems analysis when I was getting my degree in college, I can tell you that the tiny little butterfly effects that you have at the edge can have massive repercussions across the entire system. When you think about something like the supply chain of a company like Amazon or Walmart, you don't want to monkey around with those things to optimize if you don't have to. I mean, we've all heard the story of the software that is used by companies like UPS that have determined that the most efficient supply chain is the one that doesn't include left-hand turns for their trucks because they save a massive amount of time. Well, how much did that model have to predict that back in the day when it was written, when we could potentially have a digital twin that could let us operate on it and find out, okay, well, what if we permit 10% left turns? What if we restrict right turns, but only in these specific locations? I mean, we can get a lot more information out of it. And because we're twinning an actual live system, every change we make that improves or reduces functionality or efficiency will be immediately reflected in the twin. The idea behind digital twins is fascinating because we are constantly getting better at analytics. We're getting much better at capturing data and processing it rapidly. When you think about the amount of data that typically comes out of the modern vehicle, like I said, a Tesla, or even something as large as an Airbus A380-800 airplane, it's multiple gigabytes of data per hour of operation. The data dump that occurs in an Airbus when it lands is very impressive. Now, what if we could take that data, model that airplane as a digital twin, and then say, okay, we think that the engine in this airplane is exhibiting these characteristics and will fail in this amount of time? There's a huge safety concern. But we can't do that unless we have a way to process, analyze, and containerize the data in such a way as to not overwhelm our systems. That's where things like the cloud come in, being able to offer the kinds of processing necessary to make digital twinning something that can actually happen. As we improve upon our compute capabilities, as we gain the advanced capability of writing algorithms that are able to sift through the data and find exceptions to these rules, as we're able to make even better digital twins of devices going forward, it increases our capabilities of building better physical devices, being able to secure them and patch them on a more regular basis, and ensuring that our attempts to make things better don't actually make things worse. Whether it's a pacemaker or an airplane or a 45-year-old space probe at the fringes of our solar system, digital twins give us a better capability of making things a little bit better. All right, that should just about do it for this episode of Tomversations. Thank you very much for tuning in. I hope that this emerging technology idea was fascinating, and I'm going to have some links and show notes to some of the implementations of digital twins from companies like IBM to get you started on this concept. We'll be back next month with another great episode of Tomversations. And if you have any suggestions for topics that you'd like to see discussed or explained here, please make sure you hit me up on Twitter. I'm @NetworkingNerd, or you can check us out on gestaltit.com for more great conversations like this, more great podcasts, and other media that you will want to consume. Thank you very much for this episode of Tomversations, and we will see you next time.